Hello everyone, welcome to the 7th lab of the semester where we will be building circuits using operational amplifiers, which is this little guy right here. Op amps, as they're normally called, are the first integrated circuits that we are going to be using this semester. What they do is they take some input signal and they amplify it. Pretty simple. Compare this to last week's lab where we use the transistor and a series of resistors to create a small signal amplifier. Well, this essentially does that same process, but it's all in this convenient package. The op amp has, or at least the one that we're using, the TLC 272, has 8 pins, and you can see their designation up here. And actually there's 2 op amps in one circuit, so we're only going to be using one of them for all of our circuits. So throughout the experiment we'll only be using these 5 pins. So let's just talk about the op amp. You can see schematically this is how it's represented. And we have 2 inputs and 1 output. So you can see that there's both a positive and negative input. What that means is that whatever signal is being put into the op amp, it comes out as a, from the V out as an amplified version of that signal. If it comes in through the positive input, then that signal is only amplified. Nothing else really changes. However, if it comes in through the negative input, the signal is flipped 180 degrees. That's why it's negative. The last 2 pins are VDD and our ground. So this is going to be connected to our power supply, and it's going to be specifying a window, or the rail as also is what it's referred to, that our signal can exist in. And this is heavily dependent on the component itself. So for the TLC 272, the allowed ranges of voltages that we can apply is 5 to 10 volts. So we're never going to exceed 10 volts for this circuit, because it's it's not good for it. All of our amplified signals, whatever they are, they're going to need to exist within this 10 volt max range. So whatever it is. So it's an upper limit on how much this op amp can amplify a signal. Let's go over the circuits that we'll be building in the experiment. So these are the 3 circuits that we're going to be building in parts A, B, and C. The first one, the follower circuit, is the simplest. We have some input signal coming into our positive Vin, and then it gets amplified, you would expect it to be amplified, and then we get an output. However, we have a feedback going from our output back to our negative Vin. So this takes this signal and it flips it. And so when we have 2 signals coming into our input, they're combined. So we have both the positive and negative, or a regular signal and a flip signal coming into our op amp. When combined, all that comes out is our original signal. So our Vin is going to look like our V out, or it should. So nothing is really being amplified in this case. So yes, like what's the point of a circuit that just puts in something and you get the same thing out? Well, op amps have a very high impedance, so it's used as like a buffer in circuits if we're going from high current and we want to transfer this signal over to something else. It's a way of doing that safely, I guess. So pretty simple circuit, and we'll discuss this in the lab, but if our input and our output are going to be ideally the same, what should our gain be? And I'll let you all think about that. All right, so that's part A. Part B, we are going to have this inverting amplifier. So now we have an input signal going directly into our negative input terminal of our op amp, and then it's being output. So, and then our positive one is just going directly to ground. So not really being utilized at all. So we have some input signal. Because it's going into the negative terminal, it's being flipped. And so as it goes out, we should be seeing a signal that is 180 degrees out of phase with our input signal and amplified. But what is this, this other resistor doing? This is called a feedback resistor. So at this fork, part of our signal is going into our op amp. Part of it is going in this other loop. So in the op amp one, our signal is being boosted and it's being flipped. However, this one is staying in the same phase. So when they recombine together, well, they're going to destructively interfere. So this resistor can limit, or can use it to control the size of that output signal. Because when combined together, this one's going to be amplified and it's going to be much larger than this one, the signal going through this resistor. So when combined together, it can regulate how large that output signal is going to be. But most importantly, it is going to be flipped. So that's an inverting amplifier. And the last one is a non-inverting amplifier, which hopefully you can, by context, understand what that's going to happen here. So our input is going directly into our positive terminal, so it's getting output, and then part of that output signal is being fed back into our negative terminal, so it's being flipped, or it's being a smaller portion of the overall voltage. It's being led back in, and again, by controlling the size of these resistors, we can determine how large this signal coming back into it. So just how in this one they were being, this one was deconstructively interfering with the one going in through the op amp. We have the same thing, except now the negative one, or it's being flipped here. So yeah. Okay. Okay. That's those are our three circuits. There's a fourth one, but it's much more exploratory. It's just kind of showing how we can use these op amps to kind of create a very interesting circuit. So it's going to be using components from the circuit board kit, and we'll get to that at the very end of the video. Last thing that I wanted to talk about, throughout this experiment, we are going to be measuring the gain, so the ratio of our output to our input, as well as the cutoff frequency. We're going to be finding the cutoff frequency. And so in part D, we will be plotting all of our gain versus all of our cutoff frequency that we'll be finding throughout the experiment to kind of find this characteristic curve from gain versus frequency for our op amps. Let's get into the circuits. All right, so I have built the voltage follower circuit for part A. Let's go through it. So right in the middle is our op amp, and our top left pin is our V out. Underneath it is the negative V in, the positive V in, our ground, and our VDD pin, which is where we will be getting our DC voltage supply from our power supply. And the other three pins are another op amp if we wish to use it. But we're not going to. We're only going to be using these 5 pins for all the circuits. All right, so like I said, this is for our DC power supply, and that's what this lead is coming from. So we have our DC current coming in, jumping from this row to this pin, and eventually it goes through our op amp and out through the ground pin, and then this blue column is ground. Over on this left red column, we have our AC input, so that's coming from our function generator. You can see here where it's linked over to our positive VN pin, where it will eventually go through the op amp and then be output. And our negative VN and our Vout are linked together, and you can see that with this red wire right here that are combining these two rows. Okay, that's the circuit. Let's go to the analysis. Okay, now that I have everything hooked up, let's go ahead and get started. So, as you can see, I'm using a slightly different function generator this time. I think this one will come up a little bit more legibly on video, so that's the only real difference. On our left is our power supply, and we are told to set it to a 5 volts and not to exceed 10 volts. And then for our input, we are asked to set our amplitude to 1 volt peak to peak, and to set our frequency to 100 hertz. Let's output that signal. And then let's auto it. Okay. So next step, I think the numbering is slightly wonky, but step 18 in the manual. Check our VN and Vout. So like always, my yellow channel is my channel 1, and my blue is my channel 2, or output. And one thing that I didn't show when I was going through the circuit on the breadboard was where the oscilloscope probes would be. But you know, I just have them linked in to where the AC signal is for the input, just on that row, and I just have it connected to the output, the Vout, for the output, the blue channel. So that's just where they are. Okay, so let's start. So our yellow, we're seeing just a plain, let's actually scale this up, so we're on this 200 millivolt scale. So what do y'all see? This is just a regular 100 millivolt peak to peak 100 hertz. No, 1 volt peak to peak 100 hertz signal, and our output is only seeing the positive half of that signal, but it's at the same scale. So the output is, oops, actually, yeah. So we're only getting half of our signal, our upper half. So it kind of looks like a half wave rectifier right now. And let's see if we, in this next part 19, or step 19, we are asked to introduce a DC offset such that our output signal starts to resemble our input signal. So let's go to offset and let's go in steps of 0.1. So, as you can see, as we introduce this offset, our signal is now being fully displayed, our output. So let me just get rid of our input because it's really not changing. Well, it's being shifted up, but the waveform really doesn't look different. Now we are getting a exact one-to-one correspondence between our input and output signal by introducing our, well, let's see how big of our output is, or offset. So by introducing a 500 millivolt DC offset, we now have our input and our output signals looking identical. Let's measure the gain. or our A sub V, also our gain. So just by visuals, I guess, our input and output signal look the same, so our gain should be a gain of 1, because our signal is not really being boosted or amplified, it's just being output. So we'll go ahead and measure it. And we can see up here that our channel 1 is 1.01 and our channel 2 is also 1.01. So, or I guess it's slightly moving around. Essentially, it's we have a gain of 1 if we take those ratio, our output to our input. And then also, in this other part, we were asked to find the phase. Well, these two signals are completely in phase, so they have a phase shift of 0. Let's move on to parts 20 and 21. So over the course of this lab, we are going to be finding our cutoffs, and or our high frequency cutoffs, I should say, and by extension our bandwidths. So, but usually when we find bandwidth, it's we have a low frequency and a high frequency cutoff, and it's the range of frequencies in between those 2 points. But one thing that we are going to see for all of these op-amp circuits is that, well, first off, we're already at a very low frequency, and going any lower doesn't really change the amplitude of our signal. Because if you remember, the cutoff frequency is this point where our gain is equal to 1 over root 2. 1 over, yeah, root 2. So, and at low frequencies, that simply doesn't happen. So our bandwidth really is going to be from 0 hertz up until our high frequency cutoff. And we're going to be finding that high frequency cutoff for these different op-amp circuits. So let's start by finding this high frequency cutoff at this 5 volts DC. So also, which is also our -3 decibel points. We haven't really used decibels since our RC circuit lab, but taking the 20 times the log of our gain, so 20 times log of what will be 1 over root 2 will give us something that's roughly -3 on that scale. So either is good. So, but we are looking for a point where our output is going to be roughly 1 over root 2 times its current value, because this is, it's having a maximum output value of about 1 volt. So let's figure out where that should be. So this first one shouldn't be too hard to find, because again our gain is about 1. Our lab manual does warn us to not be afraid of getting into the megahertz range. So let's see if I can change the scale. So right now I'm in 7K, in like the 10K range. Still nothing's really changing. Maybe our output's changing slightly. Kind of in this 600. Okay, so I've now reached the megahertz range, and I could say, let's even this out to some good numbers. Yeah, we can go a step to 1,000. Let's see, or maybe even 10,000. I would say definitely around here is when our peak is starting to, our output is amplitude is getting noticeably smaller than our input. So let me get the measure going just to get a rough estimate. And again, our ratio should be 0.707, and because our input is roughly 1 volt, it should be around when our output is around this. Okay. I think I'm gonna cut away for just a second. I mean, to kind of. Well, okay. Well, let me show you, and then if it gets too long, I can trim it down. But kind of a combination of using the measure feature and also the cursor feature that you saw me use last week, I think is pretty good. So just to measure our input signal, we're measuring about 1 volt. So that's pretty nice. 1 volt peak to peak, that makes it pretty easy. So hopefully our channel 2 is measuring 0.707 or 707 millivolts. Let's get this cursor B down there. That's not bad. I think I've kind of. Let me actually increase the scale, kind of shift it down, just so we have a better precision in our. Whoops, not you. You stay. Let's increase this. Move that up there. Just ever so slightly. This is the. Actually, this is like 680. So I guess let's decrease our frequency because we want something that's slightly bigger, and we can shift this down, line that up, move this down. All right, we're getting there. And this is what I'm talking about, how I might, I'll show the entire process right here for this one since it's our first one, but I might cut away and just and come back to it when I found it, because it's just me. You're just watching me kind of fiddle with dials and numbers until until I actually get on the right number, which is maybe a little tedious to watch. But I'll say that's pretty good. 0.7 or 708 millivolts. And we just saw that our input signal was right around 1 volt. So that's really close to that. I bet probably as close as I'm going to get for this measurement. Let me, out of curiosity, let me go back to channel 1, see if it's still 1 volt. If it's not, I'm going to be really sad, because that means I'll need to change things around again. Yeah, it's about 1 volt. Maybe ever so slightly off. 0.92. That's okay. That's fine. Okay, so we'll say our cutoff frequency is at 1.48 megahertz, and it doesn't actually ask us to record the value for it, but I think based on our numbers, I think 1.48 is a pretty good, gets us pretty close. Okay, now in this part 21, we're asked to increase the DC voltage on our power supply and find that cutoff frequency. I don't want to change the current, I want to change the voltage. So let's see what happens. So increase, and we can see that our output signal, its amplitude has increased. So if we start, so it's approaching, oh, hello, calm down, it's not that serious. Really? Still? I don't want to have to maybe if I put you right on the center. What are we measuring? 0.976 and 0.68. That could be close. That's probably around here. Okay, I'm gonna cut away real quick, find it, and I'll be right back. All right, I'm back. So I think this is it, 2.05 megahertz. Just to show you, I'm getting a delta V, a peak-to-peak voltage of about 984 millivolts. And if I switch over to channel 2, just to adjust it, and I'm getting this is to be around 696. So those two put together are 0.7073, which is really close. So that'll be our cutoff frequency for our voltage follower for 10 volts. Okay, that's it for this part. And then, okay, and of course, you can convert this to, this is the same as our -3 decibel point. But anyways, so this is our, these are our two frequencies for our voltage follower part. So let's jump over to part B, and I'll show you the circuit. Okay, here is the inverting amplifier for part B. Just going through it real quick. Our DC signal from our power supply hasn't changed. We still have it coming on the right side, going through this pin, coming out from ground on this side. But now our positive V in is tied directly to ground. So you can see that here with this orange wire. Our negative V in is still getting an AC signal from our from our function generator, but it's passing through this R1 resistor, which is a 1000 ohm resistor, and that's going to our negative V in. And our V in and our V out are once again tied together, but this time with this RF resistor, which is a 10,000 ohm resistor. Let's go ahead and measure those, and I'll put them back in the circuit. Let's do that. Let's take those out. So our 1000 ohm resistor is really 985 ohms. And our 10,000 ohm resistor is 9.89 kilo ohms. Okay, with that, let's go into the analysis. All right, so now that everything is hooked up, we need to set our frequency to 10,000 hertz. We need to set our amplitude to 0.5 volts peak to peak. And then we need to do a negative 2.5 DC offset. All right. I think everything is set up. Great. Okay. Part 2. We should notice that the output waveform is clipped, which it definitely is, our channel 2, our blue channel. And essentially, we don't have a large enough window. Our boosted signal is too large, or it's amplified to a degree that our that it is outside the bounds of our DC window. So if we start to increase our voltage from our DC power supply, we can start to see that indeed the full waveform emerges. So I think 6 volts is enough. All right. And so now, what is our maximum voltage? Well, let's see, let's measure it. So we are reading a, let's move this up here. Let's move this up here, increase it once more, increase this one as well. All right. So, what do we see? Let's measure our 2 waveforms. So we're seeing a 5 volts peak to peak for our output, and then somewhere, it's kind of moving around, so let's use our cursors to measure our peak to peak voltage for our channel 1. And again, it's primarily because it's a pretty small signal. Seems about right. Oops, wrong cursor, wrong knob. Let's put that back. Move this. All right. And so we are seeing at 10,000 hertz, our output is 5 volts, and our input is 0.48 millivolts. At least that's what we're reading on our oscilloscope. All right. Let's see if we kind of change around the frequency of our, if we can increase the maximum, increase our max output voltage. And that looks like it's getting smaller. So it looks like we're pretty close to our max already. Decreasing the frequency, let's just see. Now that's starting to get smaller too. All right, so 10,000 is already pretty close to the max. Maybe we can make it ever so slightly higher. So let's bring out the cursors again. Channel 2. Oops. Channel 2. Here we go. Cursor below, cursor above. And then, so that's right at 5. Let's see if it gets any. That looks like it's getting smaller. So I would say that our maximum output, let's see, I could even, yeah, no, okay. I think our maximum output peak-to-peak voltage is 5 volts. So, what does that mean for our gain? Well, let's take the ratio. So 5 over 0.48, well, gives us a gain of 10.42. So roughly factor of 10 increase from our input signal. Okay. So that's part 3. Let's talk about part 4. So take an image of the waveform, make sure that they are on the same volts/division scale, and you will need to have it so I can adjust things so you can just take a screen capture. Wonder if I can, well, I can auto it to get rid of the cursor, but now I have to slightly to make everything nice and pretty. Okay. Oh, but it says to have the same division. So the two signals now are at the same scale. You can see that our output signal is roughly 10 times as large as our input signal, and it looks like it is 180 degrees out of phase. So our op amp is both inverting and amplifying our signal, as the name suggests. So in this next part, we're actually asked to measure this phase shift. So let's go ahead and do that. And I think I already have it kind of, down right here. So we are seeing a phase shift of around 180 degrees. I think it's, we'll call it that. 182.9, so very close to 180 degrees out of phase. Now let's find the cutoff frequency. All right, so if our maximum gain is at 10.42, then at the cutoff frequency our gain should be 1 that times 1 over root 2, which is 7.36. And assuming that our input voltage stays around this 0.48 mark, I think it'll probably increase slightly, but we'll just use 0.48 for right now. Then if we multiply this number times 0.48, this 3.53 should be roughly what our output voltage should be at our new cutoff frequency. The real number that we can keep in mind, though, is my thing's so dusty. The real number that we can keep in mind, though, is that our gain at the cutoff frequency should be 7.36. So maybe we'll have to adjust some values, but that's what we're shooting for. And then ballpark number we're looking for when our V out is 3.5-ish. So let's start increasing our frequency. Starting to decrease. Actually, that's not bad. We're getting there. 200, 3.68. Oh, but you can see our input voltage has gone up slightly. So it's not. It was at 0.48. Now it's at 0.492. All right. Well, it's going to be around this. It looks like it's going to be around this 200 kilohertz range. So let me pause real quick, and I'll find it, and I'll be right back. All right. So after fiddling with the numbers a little bit, I think I found our cutoff frequency to be 197 kilohertz. So our input voltage now, going by the cursors, is 492 millivolts, or 0.492 volts. And for our channel 2, our peak to peak was, let's go up here, I'll just adjust it so you can see. There, and there. Around 360 or 3.62. So our ratio, our gain at this point is 7.36 if you round, and that's very close to what our cutoff gain, or our gain should be at our cutoff frequency. So, because again, the number we were looking for was the 7.368. So we'll go with that number for this part. Okay, so for part 7, we are asked to determine the formula for the voltage gain control by manipulating equations 1 and 2 from the pre-lab, or the pre-lab section of our lab manual. So if you look at equation 1, it's given, it's an equation that gives our V out as equal to this A sub O, which is the open circuit gain.
which is all of, or open loop gain, I guess, which is a very large number. And all of these circuits that we're building, they're closed loop setups. So, but this is kind of a universal equation. But anyways, so we have, if you look at equation 1, back at the beginning of the manual, it's V out is equal to A times the quantity V, or positive, Vn minus our negative Vn. And then looking at equation 2, we have that our negative Vn is equal to 1 over our Rf plus Rn times the quantity Ri times V out plus Rf times Vn. And using those two equations, we want to find the gain equal to these resistor values. And I'll leave this to you, but to kind of, put you in the right direction, looking at equation 1, our gain for our open loop system is very large. It's a huge number. And so we're not just going to be substituting one equation into another equation and solving for our V out over Vn. We have to make an approximation. And the important factor is that in equation 1, A is a very large number. And then one other thing that we kind of have to think about, if we look at, this is just the circuit diagram for part B. Well, if we look at our positive Vn channel, it's going straight to ground. So if we were to put a value to that quantity, it would be 0, because the voltage difference between here and ground it's 0. It's ground. So for this particular circuit, this inverting amplifier, our equation really is V out is equal to A times negative Vn, the negative V internal. So with that in mind, if we make that substitution into equation 2, with the understanding that A is a very large number and some things kind of fall off to 0, you should be able to solve for it. In this next part, if you look at part 8, we are asked to, given that we know what this equation is, find a new resistor such that our gain is around 30. So previously, when we just did this, our gain was around 10. And we're going to be substituting the 10,000 ohm resistor for a 27,000 ohm resistor. So maybe this is also pointing you in the right direction. I think the lab manuals suggest that we can use the potentiometer, but I'm just going to grab a resistor that's kind of close to the value that I want. So I'm going to be exchanging our 10,000 ohm resistor. The circuit's staying the same, but the 10,000 ohm resistor is being exchanged with this one that's 26.64 or 65. 64. I'll leave it to you. Kilo ohms. And so that, with that substitution, we should be getting something that's relatively close to a gain of 30. Maybe it's a little bit small, but okay. All right, I've switched out the two components, and I've set our frequency back to 10 kilohertz, and our amplitude and offset is still the same. And now we can see with the larger resistor that our signal is once again clipped. So let's see if we can increase the voltage enough so that we can see the whole signal. And we can't. We can, but the lab manual repeatedly says to never increase our DC voltage to over 10 volts. So this is beyond the with this size of an input signal, our op amp can't output this, given that this is a limiting factor. So instead, now we need to decrease our input signal so that we can fully see our output. So it was at 500. I think let's go to 300 and this to 150 and see how that looks. It's not bad. I can see it now. All right, so that looks good, and now we can see it. So let's see what our maximum gain is. Bring out the cursors again and kind of see if we can measure our signal. Just to give a quick look, 10,000 is probably good as far as our finding our max signal. Yeah, that's fine. Okay, so let's measure our two signals. There and there. You can also measure it. So I'm reading 292. So we'll go with this 0.292 for our input, and then for our output, let's switch right there and right there. So 8.08. Okay. If that's the case, oops. So 8.08 divided by 0.292 gives us a gain of 27.67. Okay, so same gain. Our gain at our cutoff is going to be 19.56, and I'm going to assume that our input signal is going to slightly increase as we get to a higher point, so I'm going to multiply it by 0.3 instead, and so our output, yeah, this one's dusty, our output is going to be around 5.86. So let me go find it, and we'll be right back. Okay, I think I've found it. So around 86,000 hertz. So we initially said that the gain at our cutoff was going to be 19.56, around there. And looking at our cursors, this amplitude of our output signal is 5.8 volts. You can even measure it. And what am I looking at? Channel 1. If we adjust, channel 1 is the real one that I need the cursors for because it's a small signal. It was, yeah, around 2.96. So 5.8 over 0.296 gets us to 19.59, which is, I don't know, 300ths of a way. I think that's pretty good. Okay, so we have our gain and our bandwidth for this new inverter, or inverting amplifier op amp. Okay, So with that, I think we can move on to part C.
All right, here is our non-inverting amplifier for part C. So, main distinctions now is that our positive Vin is being tied directly to the input, so AC input signal on the left going into our positive Vin pin. And now our negative Vin is tied to ground with this 1000 ohm resistor, and it's still the same 1000 ohm resistor from last time, so it's 985 ohms. But now it's being linked to our Vout via this 100 kilo ohm resistor. So let's go ahead and measure this. Okay. So our actual resistance value is 98 or 99.0 kilo ohms. All right, let's start the analysis.
Okay, everything is hooked up now. So looking at the second step, we want to set our input voltage to 100 millivolts. So we'll decrease that. We want to set our frequency to 1000 hertz, which it is. And then we are asked to decrease the voltage and apply a positive DC offset such that we see our wave being displayed. So right now, and it doesn't specify what DC, well, okay, it doesn't specify what to set our power supply to, so I just set it to 5 volts, because that's kind of been where we've started in the last two parts. But we can see that given this window of 5 volts, our amplified signal is clipped, so it's not being fully displayed. So in the previous parts, we increased the size of our window from applied by our DC power supply, so that we could fully see it. What we're asked to do in this section is play with our amplitude and offset such that we find values that will fit in this specified region. So let's do that. So we'll start with 100 and start going down. And actually, let me bring this down here and this up here. So I've decreased it some. Let me increase our offset, and that should cause our okay. So it's still being clipped, but it looks like it's halfway in between now. Let me start decreasing. Actually, that looks good. Okay, so now with our new parameters of 40 millivolts peak to peak and an offset of 20 millivolts, positive 20 millivolts, we are getting a signal that is completely displayed. Great. Now let's find the gain and the bandwidth. To find the gain, we need to find our max output. So my guess is it's not going to get kind of how we've seen in other sections. The gain is pretty close to its max around our starting. Let me get rid of this. So let me see. Okay, it's only decreasing. All right, so this is at 1000 is probably where we're going to get our maximum. So let's measure this.
I'll use the cursors. So our max output, just this. Okay, so our maximum output voltage is 4.08, and let's measure our input. So let me just check. It should be around 40, but it's going to be a bit distorted, so this is definitely a case where we'll want to use the cursors to measure our signal. Even then, it's going to be kind of hard. Okay, so best we can, kind of right there. Sure. We can call it 42 millivolts. I think that's more or less kind of getting our range. So 4.8 divided by 0.42 gets us a gain of 97.14. With that, I guess one thing that we can also do real quick is before we find the bandwidth, we can find the phase shift, which this is a non-inverting amplifying setup, so I'll give you a quick guess as to what we should see as our phase shift. And unsurprisingly, it's close to zero. It's bouncing around, and that's more so because of the noisiness at our low amplitude signals. Okay, again, to find our bandwidth, 1 over root 2 times our gain, our max gain, so that gets us 68.7. And then assuming that our input voltage stays around 0.042, then our output amplitude should be around 2.88 volts. So let's see if we can find that. Let's stop this. And what did I say, 2.88? Okay. It's probably going to be around here. And then, well, 2.92. So that's pretty close. Let's see if our other signal looks the same. So let's stop that. Let's measure our channel 1 once more. It's a bit more defined. Okay, so and now it's showing 0.44, so it's changed very slightly. So let's do this calculation once more with knowing that our input signals peak to peak is going to be 0.44 at our close to our cutoff frequency, so times 0.044. So 3.02. This might be close. All right, so all right. So that's still the same 0.44. Let's get rid of this. Measure this. So what I'm reading is that at our peak-to-peak voltage is 3.02 volts at 18 point, I'm sorry, not our peak, our cutoff voltage is at
18.6 kilohertz. So 3.02 divided by 0.044 gets us close to that cutoff frequency that we calculated. So we'll say that our cutoff frequency is 18.6 kilohertz. Okay, great. In the next part, we had a gain close to 100, it was around 97. So in this next part, we are asked to change out our resistors such that we get a gain of around between 500 and 1,000. And we can use equation 4 in the manual to find that value. So looking at equation 4, just real quick, we have that our V out is equal to V in times the quantity 1 plus R2 over R1, where R2 was our 100 ohm resistor and R1 was, or our 100K resistor and our R1 was our 1K resistor. So our gain is equal to 1 plus the ratio of our resistors. So what I will do is I will pick a resistor. I'll switch out our 100K for a resistor that gets us in that desired range. And I've chosen this one, this 500 and, wow, that was really blurry. 560 kilo ohm resistor. Sorry. So let's measure this one and put everything in. So, let's see if I can angle this right. So there's our values. So this new resistor, our new R2 resistor, is going to be actually 56, or I don't know, 0.562 mega ohms, or 462 kilo ohms. All right, let's make the switch and do this one more time. The new resistor is connected, and so let's take a look. Okay, well, let's set our frequency back down to 1000 hertz. Re-auto it. And again, we need to find a amplitude, a peak-to-peak voltage, and an offset such that we're seeing our signal. And because our gain is increased, which means our signal is going to be, even more increased, or even larger, but we're keeping our 5 volts DC constant, we're going to have to decrease the values of our peak-to-peak voltage. So let's try that. Let's set our offset back to 0 for right now. Actually, 0 is really close. So, okay, that looks good. All right, so when our input signal is 6 millivolts peak-to-peak with an offset of 3 millivolts, we get a fully displayed signal. So, so for this step, we found our resistor values. Let's see, R1 was still that 980 resistor, or 980 ohm resistor that we've been using for all these circuits. R2 is that new 562 kilo ohm resistor, and our Vn is 6 millivolts peak to peak with a 3 millivolt offset. And now we're going to find the gain and the bandwidth one last time. So one thing that our manual suggests is that we don't actually try to measure this signal because it's so small, and you can even see like the it's small enough to where the background noise is interfering with the quality of our signal. So we'll just take this signal to be 6 millivolts peak to peak, which makes finding the bandwidth very easy. Okay, so let's go ahead and let's find the gain. So we don't really need to display this anymore. will put this in the middle just to double check to see if our frequency increases. Let's put our cursors. So I'm measuring a delta V of 3.2 volts. I guess 3.16. So 3.16 divided by 0.006 gets us 526.6 repeating. Okay. So that is our maximum gain. So very good. 500. So right around that 500 round. All right. So again, if this is our maximum output voltage, then finding our cutoff frequency, because we are assuming that our input signal is not changing now, we can very easily just take our maximum output divided by √2, and so when our signal is at 2.23 volts, we know that we've reached our cutoff. And so let me just go ahead and kind of adjust our, and then we'll kind of start increasing the frequency until our signal looks like it's in that range. And actually, we already found it, or near enough. All right, I'd say that's pretty good. All right, so at our cutoff frequency is now at 3.9 kilohertz, because it's measuring, again, our peak-to-peak voltage of around 2.2. We can see as we've increased the gain of our system that the cutoff frequency has decreased, so our bandwidth has gotten smaller. In part D, we are asked to display a plot of all of those gain values at their according cutoff frequencies. So you should have 6 data points, and the idea is to plot the gain on this logarithmic scale, the 20 log of our gain values, and set that equal to the corresponding frequencies, and have that be on a logarithmic scale too, since it spans a very wide range of frequencies. But that's pretty much it for the data analysis part. The last circuit, part E, is just exploratory. It's just something that you can do with op amps and some stuff on the boards that demonstrate the capabilities of the integrated circuit and some other things. So I'll jump to displaying that, and I can show it. But other than that, that is the data collection of this lab. All right, everyone. So this is the built circuit from Figure 4, or I guess it's called Circuit 4 in the lab manual. Just kind of go through a couple things. We're getting our power from our power supply. It's off screen, but it's around 3 volts. Over here on our left is our potentiometer. It's in our R1 resistor spot, so right now I have it set to its minimum value. And over here is our phototransistor, so it takes it outputs a small signal depending on the amount of light that it is receiving. Down here is our transformer, which is taking our signal from our op amp that's being boosted from our op amp and transforming it into over where the speaker's at down here. So it's taking this small AC signal from our photo
transistor and turning it into a mechanical wave that we should be able to hear. So I actually have it on right now. I'm not sure if you can hear it. It's very, very faint. I'm not sure if the audio on my phone will be able to pick it up, but let's see what happens when I start to change the potentiometer. Can you hear it now? So the potentiometer is acting kind of like our volume switch for our sound. So it's increasing the gain of our signal that's being boosted. And let's see what happens if we give the transistor more light. So I'm bringing in a flashlight, and now you can definitely hear it. It's actually kind of annoying. Maybe like a R2 scream. Anyways, so as we give the transistor, or the phototransistor more light, we get a much more high-pitched sound. Okay, so anyways, that's just giving an example of the things that you can do with an op amp. I mean, we could have built this without using this integrated circuit, but it would have been a lot, very complicated. All right, that's it for this lab. I will see you in the next one.